Okay, so welcome back. We're going to continue lesson 4, measures of center and spread. Before we move on to measures of spread, there's one more item that I forgot at the end of the mean and median lesson, and that is comparing the two. In other words, which one's better? Mean or median? Which one should you generally seek to use? Now, in a lot of cases, you can use either, but there are important differences, and I want to use an example to illustrate that. So, suppose you have 9 people working at a small company with the following commute times. Find the mean and the median of this data. So, let's just call this, we'll call this part A. So, we'll call this part A. Find the mean and median. The mean, we're going to add up. So we're going to get a total of 216. We're going to divide that by 9, and you get an answer of 24. Always make sure you use units. So the average commute time or the mean commute time is 24 minutes. Now the median, which I'll just use an M for. Well, we have, let's see, we got to sort these now. Okay. So the median, there's 9 of them, right? So the median is going to be that point in the middle, the 23. So that we see, this is pretty symmetric data. There's not a lot of outliers or unusual data points on either side. So the mean and the median are about equal, pretty close. I want to illustrate a situation where there is a difference. Suppose a 10th person is hired with a commute time of 115 minutes. So maybe they're a telecommuter, but in any event, they have 115 minutes. This is the crucial difference. So I'm going to find, again, the mean. So we already found the sum of the first 9. So we just add the 115 to that, and that's 43.1 minutes. Now the median, so that's a big difference, 24 minutes to 43.1 minutes. That's a huge difference. What's that going to do to the median? Well, the median, now we have 10 data points. And so the median is going to be the average of 23 and 26, the numbers on either side. So it's going to be 49 over 2, 24.5 minutes. So I want you to notice the difference. When we add that very high outlier, that 115, the median changes a little bit because we're going from the 5th data point to the average of the 5th and the 6th. So the median's going to change a little bit, but look what happens to the mean. Look what happens to the mean. It's a huge difference going from 24 all the way up to 43.1. So the way we would express this is we would say that the mean is sensitive to outliers. So if you have outliers in your data, in other words, if you have a skewed data set where you have an unusual data point to the top or to the right or to the left, probably want to go with the median in that case. It's going to be a better picture of the data. You know, if you notice when you look at things like salary data, particularly housing prices, they don't talk about the mean housing price. They talk about the median housing price, because what's going to happen is if you have a bunch of houses that are, 200,000, 250,000, and then you have a couple of $5 million mansions, those mansions are going to pull up the average, and they're really going to kind of give you a skewed picture. But if you're talking about the median, then just adding 1 or 2 large data points is not going to affect here, down here, it's not going to affect the median as much. But an unusually high data point is going to be the mean's going to be very sensitive to unusually high or unusually low data points. So if that's the case, if you have outliers to the right or to the left, then you generally want to use the median. If your data is symmetric, then it doesn't matter as much. The mean and the median are at least approximately equal, as we saw when the data was more homogeneous. Okay, that brings us to the last part of this lesson, and that is measures of spread or variability. So we found the mean. We found, what we think of as the average data point. There's another measure that has to be taken into consideration. If you look at the plots below, and these plots, this is something called a dot plot. I didn't cover it here. It's basically just another form of a histogram. Instead of drawing bars, you stack up dots. It's basically the same thing. Now, these two data points both have a mean of 40, a median of 40, and a mode of 40. They both have the same mean, median, and mode, and yet clearly they're not the same data point. The data set on the right is a lot more spread out, and we need to account for that, particularly when we're finding inference. We're doing data inference. If your sample is all over the place, it's going to be harder to make a prediction than if your sample is all over the place, it's going to be harder to make a prediction than if your data is relatively homogeneous or relatively stable. So the standard deviation is a way to quantify that difference. Set 2, the set on the right, is more varied, and we need to quantify that. And that's what the standard deviation does. Now, I'm going to show you the formulas. I'm not going to get too far into the formulas here. I'm going to find standard deviations by hand in this lesson. In the future, we're generally going to be given a value, or we're going to use technology. But again, I want you to at least see where it comes from. So again, don't be freaked out. I know it's easy to say, but I'm going to go over this. And really, we're going to use this formula a lot more often. Now, you notice, just like for the mean, you have two different symbols, and this is important. So if you have a population, standard deviation, the mean of a population is the Greek letter mu, the sample is x bar. Standard deviation is the lowercase Greek sigma, and the sample is just s. So again, you should be somewhat familiar with the symbols, even if not the formula themselves. Even if this was a regular stats class, you would have a formula sheet for this. So it's not necessary to remember the formulas. But you do notice, I do want to point out one thing, and that there is a slight difference. Finding the mean was the same process, population versus sample. Finding the standard deviation, there's a slight difference. And n squared versus n times n minus 1. And the reason for this difference is that when you're finding a standard deviation of a sample, there's more uncertainty because of the sampling error. Right? The sample is not the same thing as the population. So to account for that, we deliberately overestimate the standard deviation. So a smaller number. Divide by a smaller number, which means we're going to overestimate. We're actually going to get a larger number for S than we do for sigma. I'm going to use the sigma form. I'm going to stick to this because, again, for the same reason that I did use samples for the mean, because generally when we do these calculations, we're working with samples, not populations. So it's a good thing to get used to. I'm going to do just a quick example with finding standard deviation using the formula. Again, you can, if you're not algebraically inclined, feel free to skip this. But I feel I'd be doing a disservice if I didn't at least show the formula once. So let's just take some generic data here. We'll keep it simple. 0, 1, 3, 8. So let's kind of see what we're going to put into this formula. N is equal to 4 because there are 4 data points. Now, I want to distinguish between these two. This over here, sigma of x squared, means we're going to square all the numbers and then add them up. So I'm going to take 0 squared plus 1 squared plus 3 squared plus 8 squared. And that's going to be 1 plus 9 plus 64, which gives us 74. Now this number over here, we're going to take, notice the squared is on the outside of the parentheses, meaning that we're going to add the numbers first and then square them. So it's going to be 0, 1, 3, 8, and then square the whole thing. And that's going to be 4 plus 8 is 12, and that's going to equal 144. So that's the difference between those two. From that point, we're just plugging numbers into formulas. And this is almost as sophisticated as the math is going to get in this course, in terms of difficulty of formulas. You'll see a little that are bigger than this, but I mean, there's not a lot of algebra, as I said. We're not going to be doing a lot of fancy equation solving or factoring or any of those types of things. So let's just put this in. You have n is 4. We have 4 data points. We found the sum of the squares. And that was 74. And then we have the sum then squared. That's minus 144 times 4 times 3. So if we put this into a calculator, that's going to give us 12.67. And then if we take the square root of that, and so 3.6 is the standard deviation of that population, of that sample. Now, you may be asking yourself right now, so what? What does that really mean? I mean, a mean or an average, you kind of have an intuition for. Standard deviation, not so much. And again, first of all, if you're not completely clear on the calculations we're doing here, that's perfectly fine. Like I said, I want to at least give you some exposure to the formula, those of you who are more mathematically inclined. For the most part, going forward, we're simply going to be given a standard deviation. So, like I explained in the opening lecture, it's not so much about the calculations, but knowing how to interpret them. And with that said, what does a standard deviation of 3.6 mean? Well, the standard deviation by itself doesn't mean that much, but it has meaning when it's used together with other statistics, such as the mean. So if I hand back test papers to a class, if I say the average is 82, or the average is 60, you have an intuitive idea of what that means. 82 is good, 60 is bad. If I hand back test papers and say the standard deviation was 17, you might say, well, so what? That doesn't have much meaning to me, and you'd be right. That by itself means very little. But we will see in later lessons where we use the mean and standard deviation in conjunction with other numbers to calculate some more sophisticated or more meaningful numbers, meaningful statistics. So that's where I'm going to leave standard deviation for now. Basically, what you need to understand for standard deviation is that it's a measure of the spread. The higher the number, the more spread apart the data is. In the extreme example, if I have another set of data, let's say 5, 5, 5, 5, 5. If all the data points are the same, the standard deviation is going to be 0. There's no variance among them at all. If we put it into the formula, we'd find that out. Okay, so I want to finish up. We talked about center versus spread. And I want to show you just some examples here. Now, what you see here, these curves represent histograms. And we're taking the bell curve. Basically, we're taking the histogram and representing it as a bell curve. So we're not drawing out the original rectangles. We're just keeping it to an approximate curve. And we're going to learn about bell curves. We're going to learn more about bell curves later. So for the time being, these are just representations of histograms. If the data sets are identical, you're going to have the same mean and spread. The same, and by the way, with a bell curve, the mean is equal to the median by default, but by definition. So I'm kind of using those interchangeably. Basically, the mean and the standard deviation, if this represents two identical sets, then the mean is equal to the standard deviation. The location, so these have the same spread, but different means. But the spread is the same. The standard deviation is the same, so you can see they have basically the same shape. Standard deviation is a good way of referring to the shape. Here, we have the same mean. The data is centered in the same location, but different standard deviations. This one, call it number 1, call this number 2, and we can say that standard deviation for 1 is less than the standard deviation for 2. You can see it's tighter, it's more concentrated around the center, and of course, in the last case, you have both of them differ. So the mean refers to the location of where the data is centered. And the standard deviation for a histogram kind of tells you the shape, all else being equal if we assume it's a bell curve. And like I said, we'll talk more about bell curves later on. Okay. So that will bring this lesson to a close. So we talked about a lot of things. We talked about measures of center, measures of spread, and we found descriptive data, descriptive statistics about a data set to tell us where the data is centered and how it's spread apart. So in the next lesson, if you're a little confused about what I mean by shape and center and spread and all that, because I made some references to shape of the data and outliers. In the next lesson, I'm going to clear that up a bit, and we're going to talk about shapes of data sets, shapes of distributions, and how the mean and standard deviation and median all fit together. So thank you for watching. I'll see you in the next video.